Hi, welcome to the course Machine Learning with Python. This is the third module. In this module, we will learn exploratory data analysis, feature engineering, and hypothesis testing. So let's have a look at the contents that we would cover in this module. We can broadly divide the contents into two sections. In the first section, we'll first start with an overview of the machine learning methodology and then understand exploratory data analysis in depth. We'll then conclude section 1 with feature engineering. In section 2, we'll start with a brief introduction to statistics and then move on to learn statistical inference and probability distributions. Finally, we'll conclude section 2 and the module with hypothesis testing. Now, statistics is a vast topic and covering each and every component in statistics that would be required for the machine learning course is beyond the scope for this course. So we will be covering a couple of important terms that would be required in this module and the forthcoming modules at a high level. So we will be abstracting the complexity of math to a certain extent and keep things short and brief. So let's get started. So let's begin with the machine learning methodology or the machine learning framework. Now, any typical machine learning use case or the process involved in solving a machine learning problem can be logically divided into 5 simple steps. It starts by identifying the problem, then gathering the data, performing EDA and building features, or in fact understanding the data, then building the machine learning model, and finally productionizing the solution. Let's get into the depth of it. So, identifying the problem. Typically, a machine learning methodology or the machine learning process is actually a part of a larger problem. So let's say you are a retail giant and you have a problem, identify the problem like the sales are going down or the overall revenue for the current year has been significantly lower than the previous year. And you're trying to understand what is the problem. So this is the larger problem. Now in the process of solving the problem, you understand that the sales and the revenue are actually low because of customer churn. So a lot of customers have been churning out in the past year and the current year. So you want to understand how can you stop customers. So you want to build a machine learning model that can go and predict when a customer will churn or not. So this is a specific problem inside a larger problem. So the larger problem will be sales are going down, and a specific problem inside that would be customers are churning, and you need to actually find out a way to stop customer churn. So when you understand machine learning methodology and you're building a machine learning model, you're actually solving a specific problem within a larger problem. So the process first starts by identifying the problem. Now, in the example which we have been detailing about, identifying the problem will be building a machine learning model for predicting customer churn. So you're predicting when a customer will churn out from your retail chain and so on. So once you have identified the process or identified the problem clearly, the next step would be to gather the required data to solve the problem. So let's go back to the same example. You're trying to predict when will a customer churn, and for this problem, what kind of data would you need? You would need customer related data. So what kind of customer demographics are there, customer transactions? There might be a loyalty program associated with the customer, the kind of points he has earned and the kind of points he has burned. Then there's a store locations are there. So there are store level data. The store has a planogram. So let's say different sort of products and assets are organized into different compartments of the store. When so where are these products and assets stored? So the planogram information of that, then product related information, then seasonal information. A couple of all, so apart from transactional data, there are several other data dimensions that will be considered to solve this problem. So gathering data, or step 2 in this process, is getting the data under one roof. Typically, in a large organization, data would be spread across heterogeneous sources and probably in different formats. So getting them under one roof and in a simplified format so that you can go ahead with the analysis is the step that naturally follows after identifying the problem. So once you have the data under one roof, the next step would be to understand the data. And that's when we have EDA. So performing EDA and building features is a step where you get the depth of data, understand what is the data talking about, understanding what is the story in the data. Now in this process, you get the true depth of the data and understand more about the problem. Building features is a topic which you will get into depth in the upcoming slides. But for now, you can understand that building features is a simplified way of projecting data in a more informative way. So once you have built features, you've understood the data, you've performed exploratory data analysis, that's when you have at the right time to build a machine learning model. Now, building a machine learning model is again an iterative step. You'll actually start with a simple model, build more complicated models or more complex models, and finally, in fact, in some cases, create several models and combine them into a single model, and then look for accuracy, a couple of other metrics that you would be interested in. And after several iterations, you'll actually reach a point where you'll have the best model for your use case. But once you finally have the machine learning model in place, you'll actually go ahead and productionize it. So productionizing will be different in different scenarios. So coming back to the same example which we have been discussing. So let's say we are solving the problem for a retail chain where the high level problem is sales are going down. And a specific problem within this problem scenario would be customers are churning out. Now, productionizing the machine learning solution might actually be building a machine learning tool, which might be a feature which goes into a larger data product, or in fact, creating a machine learning end-to-end algorithm, which might act as a standalone tool. So these are two different scenarios, and in each different scenario, productionizing the solution, or in fact making a solution robust for the future, is what we mean by productionizing the solution. So at a high level, let's have a quick recap. So we have a larger problem, and in that larger problem, we are solving a specific problem. That's when we have the machine learning methodology in process. So you identify a problem, you gather data required for that, for solving the problem. Then you perform EDA or exploratory data analysis, build features, and then naturally understand the data better. And then you build machine learning models, then finally productionize the solution. Now, in reality, all of these steps are iterative. Like it's very difficult to find the correct problem in the first go. You'll never have the right amount of data identified or collected in the first go. You'll never understand the data in a very concise way in the first iteration. And you'll never ever get the best machine learning model in the first iteration. Productionizing the solution is also an iterative and efforts-in activity. So in a nutshell, if you take up any machine learning use case, it naturally follows through these 5 logical steps. Now, in module 5, we'll actually be working with a real-life use case for a project. So in those modules, we'll actually get the depth of identifying a problem, and to a certain extent, we'll understand abstracted way of gathering the data. In the present module, we'll talk in detail about performing EDA and building features. We'll understand how we can explore, analyze, and study the length, breadth, and depth of data. So let's get started with EDA. So what is exploratory data analysis? EDA or exploratory data analysis is the process of studying data by leveraging various statistical and visualization techniques. To understand EDA in the simplest form, a layman definition would be EDA is the process of understanding the data, or in fact exploring the data. Now, how do we do this? There are 3 different ways. It's the first one is univariate analysis. Now, as the name suggests, univariate or uni is a process of exploring a single variable or an attribute at a point of time. It doesn't really explain the relationship or the causes for a pattern. So to take an example, let's say we have conducted a test among 100 students and you're trying to understand how did students score in this examination. So how did students fare in this examination? So you would have answers like the maximum score obtained by a student was 95, the lowest was 45, on an average the student scored around 65, etc. etc. So this is the process of understanding just one variable, that is the score of a student at one point of time. That's univariate analysis. Moving on, we have bivariate analysis. Again, as the name would suggest, bivariate involves the analysis of 2 variables at one point of time. and it also determines the empirical relationship between them. So let's say for the same example, you want to understand how did students score in the test in accordance with the amount of effort they've put in. So let's say you have also measured the number of hours each student has studied, and you also have the corresponding score for each student. So you would actually believe that the more number of hours invested by a student for the test, probably he would actually get a higher score. So you're trying to understand the relationship between number of hours studied by a student and the equivalent score he's got. That's bivariate analysis. Lastly, you have multivariate analysis. Multivariate analysis involves the analysis of more than one variable. Now, more than one variable because it could be two, it could be three, and it could be anything more than that. If it's two, we usually call it bivariate analysis. If it's three or more, we usually call them multivariate analysis. Uh, in fact, every form of bivariate analysis is actually a multivariate analysis. A simple example of multivariate analysis would be linear regression. We're trying to understand the impact of more than 3 to 4 variables on one variable. So let's say you want to understand how well does a student score based on his gender, his age, the number of hours he studied for, and so on. So you have many variables and one dependent variable. So that's multivariate analysis. We'll actually take up multivariate analysis in depth in the next module, machine learning. So linear regression, logistic regression, these are basic examples of multivariate analysis. For now, let's explore univariate analysis and bivariate analysis in more detail. Univariate analysis, as you would already know, is the study of a single variable at one point of time. So based on the kind of attribute you have, let's say a categorical attribute like gender, which could actually have values of male and female, or a numeric attribute like age, which could have values like 10, 15, and 25. The visualization technique and the statistic measure that you would use to interpret these variables will actually be different based on the kind of variable they are. So when you're actually studying a categorical variable or a categorical attribute, you would use a bar chart coupled with the count measure or a pie chart coupled with the count percentage measure. And this will help you to understand how is the data distributed across the different classes inside that categorical variable. So to simplify this, let's have a visual tour. So assume for simplicity that a bar chart looking like this, we have two values, male and female, and a simple bar chart where we have the values, let's say 40 and 60, indicating the frequency of records distributed across these categories. Also, let's say you have a more comprehensible version using a pie chart. So something as simple as this, we have 40 male and 60 female, and this would be in percentages. Now, this is a simple way to interpret and understand how does the categorical variable look like in the data set. Now, this is very simple because we have only two levels in the category. What about those scenarios when we have fairly more complicated categorical variables? So let's say something like class, let's say it's an abstract variable, which would have levels of A to F. So interpreting that is very difficult using simple numbers. But when you put it in a bar chart, or let's say a pie chart, things become fairly straightforward. Let's say A, B, C, D, E, and so on. Assume that we have several more. We can clearly see that two of them stand out. We have larger number of records in B and D. If you do the same with a pie chart, you can actually see that, let's say, class A or let's say class C have a larger chunk of the pie, and there are several other attributes which have a smaller chunk, let's say D, E, F, and let's say X, Y, Z. We can clearly see that there's an important component over here, and there's an important component over here. So this is how you can use bar charts and pie charts coupled with two simple measures, the count numbers, which is the frequency, and the count percentage, which is absolute percentages of the levels, to understand the depth of the categorical variable. On another note, when you're studying a numeric attribute, you will have two simple visualization techniques that will give you very informative results. The most common one is the box plot. The box plot is the easiest and the most common way to interpret a numeric attribute. So let's say when you're trying to understand something like age of the students. You have 100 students, so you have 100 records, and you're trying to understand how is this data looking like. So box plot in a snapshot gives you access to the minimum, maximum, mean, median, range, and quantile values. So what does these statistics refer to? Minimum, as simple as it sounds, is the minimum value from all the observations. And so is maximum. Maximum is the maximum value of all the observations. Mean is the average, which is the sum of values divided by the number of observations. Median would be the middle value, like the 50th percentile. Range is the difference between the maximum and the minimum, and quantile is a set of cut points that divide a set of data into groups containing equal number of values. So let's look at this using a visual tool. So let's assume that we are trying to understand age of students as an attribute. Now this is a numeric attribute. I'm using box plot to understand how does it look like. So a simple box plot can be interpreted using a simple figure. This would be the y-axis, and since this is a single attribute, this would be a x-axis. So you don't need anything on the x-axis, but on the y-axis, you would have age. Now these numbers at different points will indicate different values. So this would correspond to the minimum value. This would correspond to the maximum value. This would be the 50th percentile or the median. This would be the 75th percentile or the third quartile, and this would be the 25th percentile or the first quartile. So first quartile, third quartile, median, minimum, and maximum. Now, to understand the average from the box plot, so most plotting libraries under R and Python don't really give you a straightforward way to put the mean also onto the box plot. But using a simple technique, you can actually just fabricate this and get the mean plotted along with the box plot. So let's say in this box plot, the red asterisk mark indicates that is the mean value. So this would be the mean. Now this is how you interpret it. You actually get all these metrics visually explained, and you can actually understand how does the data look like. Let's make this more tangible. Let's say we put across some values across all of these statistical measures. So in the case of age, we say that the minimum value is 18, the maximum value is 30. The 50th percentile or the median value is around 26. 75th percentile is 29. Mean is around 28. 25th percentile is around, let's say, 24. Now looking at this, we get a fair amount of idea about the data. We know that the range is around 12 units, but like the minimum is at 18, the maximum is at 30. And on an average, the age of the student is around 28 years. So we know for sure that there's a high amount of, most of the students are mostly fall in the upper age bracket. We also see a great jump from 18 to 24. We also see a great jump, smaller jump from 24 to 26, and so on. So box plot basically gives you a basic overview of the entire data point in a single snapshot. Now, this is also the most easiest way to understand whether there are outliers. So let's say now this box plot presented over here is a fairly straightforward one. And then let's say we have a structure which looks like this. So we can see that there's a huge gap between the minimum and the 25th percentile. On the same way, let's say if we had something like this, you can see that there's a huge gap between the 75th percentile and the maximum value. So these are areas where you can see there are a lot of outliers. And similarly, the jump between two quartiles can actually help us understand where is the data distributed unevenly. Now, this is one of the easiest and the most commonly used technique to first understand a numeric data set. So, similar to box plot, we have histogram that helps us study the dispersion of data. So, if you want to understand how spread is your data, box plot alone won't really be helpful. We actually need to use a couple of other statistical measures to understand how spread is the data. So in that scenario, With the help of a histogram, we can conclude a couple of statistical measures like first variance. Variance is the fundamental measure of data dispersion, and we have standard deviation which follows from variance. Standard deviation is the square root of variance. So in a nutshell, if you take up any problem in statistics, the most popular and the most widely adopted statistical measure to explain data dispersion is standard deviation. So whenever you see any statistical example and people are talking about data dispersion, standard deviation is the de facto statistical measure used to study deviation or data dispersion. Now, along with variance and standard deviation, we have coefficient of deviation. So coefficient of deviation, if you look at the definition, it would be a measure of data dispersion divided by the mean. A more simple or a more layman explanation of coefficient of deviation would be coefficient of deviation is defined as a standardized measure to define standard deviation. So I'll give you an example to make this simple. So let's say if you have an example where I'm saying the average age of students in a classroom is around 25 and the standard deviation is around 5. So with these two numbers, you'll kind of construct a plot in your mind to study the data distribution because you have a measure to understand dispersion and you have the mean or the average age for that sample. So the standard deviation made sense because you had an idea about the mean. But what if I would just give you a number like, let's say, okay, the average height of students in the classroom has a standard deviation of 7. So without the mean, like if you have no idea about what is the mean height of all the students in the classroom, just standard deviation won't really be, like you won't be able to make sense out of this number. It's not really very interpretable. Only with the mean, only when you have access to the mean, that's when standard deviation becomes more meaningful. So to make that more interpretable, we have a structure or a standardized way where you can express this metric in a percentage format. So what if I tell you uh, the average height of students in a classroom has standard deviation of 40%. So this 40% is a number which is tangible so that you can actually kind of visually construct something in your mind to understand how dispersed is your data. So that's basically coefficient of deviation. Coefficient of deviation is calculated by dividing the standard deviation by the mean and multiplying it by 100. So you get a number which is represented as a percentage. Similarly, we have skewness and kurtosis. Skewness is a measure of asymmetry or symmetry in the distribution of data. Now, there is an important term which you would cover over here that's called normal distribution. Probably this is the first time you've heard about it. But in the upcoming slides, we take a detailed note on understanding what is normal distribution. But then for now, I can give you a simple example which will help you understand how is data distributed for a normal sample size. So if you consider, let's say the height of, let's say we have an example where you're calculating the height of all the citizens of a country. So you want to say average height of men is around 5 feet 7 inches, and the average height of women is around 5 feet 5 inches. And if you go for a plot, the overall plot for the entire sample or the entire population kind of represents a bell curve, where let's say this is the midpoint and this is the range, which is like the area where maximum people would have the height, and then a couple of outliers over here, so majority of the samples kind of fall towards the middle. That's why we have a bell kind of figure, and this is called a normal distribution. Now, coming back to the previous example or the statistical measure we have been talking about, skewness is a measure of symmetry or asymmetry in the data set. So if you look at this example, this is symmetric. Now, if we had an example where we had a plot and we have a structure like this, so we understand that it's not symmetrical and the data is skewed towards one end. So there's less amount of data towards the right and there's more amount of data towards the left. Or we could have something different. We could have a plot like it is skewed towards the left, but it has more amount of data towards the right. We can see that, okay, fine, majority of the data falls in kind of this section and little bit of data falls in this kind of section. So if you come back over here to the main example, we can understand that skewness is a measure of symmetry or asymmetry. How symmetric is your data? If your data is skewed towards one end, can I have a number which will help me understand how skewed it is? So looking at the histogram, definitely you'll be able to interpret that. But then how much you want to tangibly boil that down to a number to understand, okay, how dispersed is the data? That's when we have skewness as a measure over there. Similarly, you have kurtosis. Kurtosis is a measure of whether the data is peaked or flat. So if you come back to the same example, we can have a simple plot that let's say I'll first draw a normal distribution. And I want to draw a curve which is actually a representative of kurtosis. So the curve might be flat or the distribution would be peaked. So I'll actually understand, okay, this might not be a more appropriate one. Let's have an appropriate one. An appropriate one would be something like this. So you can actually look at this and figure out, okay, in the first scenario, when it is really peaking at one point, we can understand that kurtosis is high. It is actually peaking. In the other end, we have a scenario where the distribution is kind of flat. That's kurtosis. Kurtosis helps us understand whether your distribution is looking flat or is it looking peaked at one peaked for a specific range of values. So coming back for a quick recap, with the histogram, we can understand a couple of simple statistical measures like variance, standard deviation, coefficient of deviation, skewness, and kurtosis. With these numbers, you can actually understand how spread is your data. Like you can actually figure out the dispersion of data visually using a simple tool, or you can actually have these numbers tangibly printed or and then correlate them to a mental plot. Let's take a simple example to actually go ahead and calculate variance and standard deviation and coefficient. And then we'll actually look at a simple histogram to see how can we interpret things just looking at the histogram. So we go back to the tool. Now let's take a very simple example to calculate variance and standard deviation first. So I'll just take a simple number. Let's say we take a sample of 5 numbers, 2, 4, 6, 8, and 10. I'm restricting this example to even numbers so that the calculation becomes easier. Now, if you want to calculate variance, you can calculate variance with a simple formula as summation of I is equal to 1 to n being the sample size, mu minus x of I. Mu is the mean of the sample upon n minus 1. Now, in this case, we use n as a denominator when we are considering the population, and we use n minus 1 when we're using a sample. Now, the difference between the two, you'll mostly deal with a sample in any sort of analysis. There are cases, definitely there are cases where we have the entire population for consideration, but then consider a scenario. Let's say you're trying to understand what is the average height of men in India. So you can't literally go and calculate the average height for a billion men, a sample of billion size. You'll actually take a small sample, which is a true representative of the entire population. So you'll probably take a sample of, let's say, 10,000 members and then use that as a statistic to infer some ideas about the entire population. So in cases when you have a sample, the denominator would be n minus 1. And in cases when you have the entire population, the denominator would be n. So in this case, we use n minus 1. So let's do the math to actually calculate the variance for the simple sample. I'll use this calculation over here. Now, putting these numbers into the equation, we first need the mean. The mean can be calculated as mean is equal to, it's a simple addition of all the numbers divided by the total number of elements. So that would be 2 plus 4 plus 6 plus 8 plus 10 divided by 5. So this would be 2 plus 4, 6, 6 plus 6, 12, 12 plus 8, 20, 20 plus 10, 30. So that's 30 by 5, which is 6. So the mean is 6. So we have a number over here, first number. We can say mean is mu, that is 6. Next, we can calculate the variance. So putting the number into the formula, we will say 6 minus 2 the whole square plus 6 minus 4 the whole square plus 6 minus 6 the whole square plus 6 minus 8 the whole square plus 6 minus 10 the whole square. So the moment we have square and divided by n minus 1, which is 4. So the moment we have square, there are no negative numbers. They become positive. So in this scenario, it will be, the first one would be 6 minus 2 the whole square, that is 4 square, which would be 16. Second would be 6 minus 4, 2. The whole square of 2 is 4. Plus 6 minus 6 is 0. Again, 6 minus 8 minus 2 square is 4. So we have 4. And 6 minus 10 is minus 4. Minus 4 square is 16. We have plus 16 divided by 4. And this would be 16 plus 4, 20. 20 plus 20, that is the first 16 plus 4, 20, and then again 16 plus 4, which is 40. So 40 by 4 would be 10. So we can say the variance is equal to 10. We have another metric. Now we need to calculate standard deviation. Standard deviation is simple. It's the square root of variance. So standard deviation is equal to the square root of variance, which is the square root of 10. So square root of 10 would approximately be 3.16. So 3.16 into 3.16 would be around 9.9. But then for simplicity, let's assume 3.16. And finally, we have one more method, that is coefficient of deviation. That can be represented as 3.16, which is the standard deviation, divided by the mean, that is 6, into 100. So this would be approximately 50 to 52%. Let's take a simple number, 52%. So we have three numbers. Let's say coefficient of deviation. We have this number as 52%. We have variance as 10%, and we have coefficient of deviation as 3.16. My apologies. Let's just clear this. We have coefficient of deviation as 25%, and we have standard deviation as 3.16. So we have the first three numbers. Now, just interpreting these numbers, just try and understand how do these numbers make sense. So you have a sample for whom we have, let's say the mean is 6, variance is 10, standard deviation is around 3.16, and the coefficient of deviation is around 52%. So if you look at the numbers, I'm saying mean is 6 and coefficient of deviation is around 52%. And you can actually understand kind of how does data look like. So if it's 50%, half of the numbers will be actually towards the left and half of the numbers will actually be towards the right of the entire sample. It might look kind of a very simple plot, like a very simple straightforward plot. Like this is how you try to make sense of these numbers. Similarly, let's look at the normal distribution. So when you're talking about skewness, let's say we're talking about skewness. So we have a simple graph which might be a representative of the normal distribution. Now in this case, it's normally distributed because this would be the midpoint. But then if in case you don't have a normal distribution, you have a skewed distribution, you will have something like this. In this scenario, you can see that your tail is towards the right. So you have a skew towards your right. That's when we call it positively skewed. Apologies with my handwriting. I will say positively skewed. And in another example, let's say we have, let's say over here itself, I'll use a different color. I have a number where I have the axis, the number skewed towards the left, which is the negative part. Now this would be negatively skewed numbers. Negatively skewed. And finally, we have kurtosis, which can be represented using a peak or a kind of a flat distribution. So with these metrics, we can actually understand how spread is the data. 5 simple measures with a histogram. Now, if you look at a histogram, a simple histogram can be represented using bins. So let's say we have bins which can be defined with simple numbers, and this is how this histogram would look like. So this can kind of help you understand that this is a very normal sort of distribution. If you had an histogram which kind of represented a different shape, you can get an idea of how skewed the data set is. So this would be the kind of curve you have. So coming back to the crux of the topic, we've looked into basic numbers like minimum, maximum, mean, median, range, quantile using the box plot. And to understand more important or more advanced measures about the data set, we have a histogram which will help us understand variance, standard deviation, coefficient of deviation, skewness, and kurtosis. So the visual tour I gave you is a simple example just to give you a visual experience about how these different measures look like and how are they calculated. But how do we do this in Python? That's an important thing. So let's move on to Spider. We'll take up another simple example and we'll see what kind of functions are available to actually understand the data for a numeric attribute using these different statistical measures in Python. Bivariate analysis is the study of relationship between two variables. Now, as the name would suggest, bivariate, it clearly indicates we are including two variables in our analysis. And this might actually introduce you to three different scenarios. You might have a scenario where you're trying to understand the relationship between two numeric attributes. Another scenario where we would have one numeric and the other categorical variable. Or the last scenario where both of them could be categorical. So what statistical measures do we use, or what kind of data visualization techniques we can put in place so that we can interpret the relationship and study what kind of patterns exist between two variables while analyzing them. So we'll start with numeric and numeric variables. So the easiest way to visually interpret two numeric attributes is using a scatter plot. A scatter plot defines the correlation between the two numeric variables. So correlation is a simple statistic measure. We call it as correlation coefficient and is used to measure the strength of relationship between two attributes. It's a number which takes a value between -1 and +1, where +1 would be strongly positively correlated and -1 would indicate strong negative correlation. The example showcased over here might not be really intuitive, so I've taken the same example which we used in the previous slide. So we're trying to understand, using a scatter plot, the relationship between satisfaction level and last evaluation. So you don't really see any trend over here. So you can't conclude whether it's a positive correlation or a negative correlation or is there any relationship between them. It just looks a random mess. So just to make things simple, I'll try to demonstrate a simple example using the visual tool which we have over here. So consider we have a simple chart, a plot. We are trying to plot two variables, x and y, both are numeric. And you might see an increasing positive trend. Like, let's say you're trying to plot a simple example of, let's say, number of years of experience. This would be work experience and the annual salary package for that employee. And you would actually expect, as per the industry trend, with more number of years of experience, you would actually see people earning more salary, right? So it is kind of a linear trend increasing in a very coherent fashion. And there definitely might be exceptions. There might be a person with less experience but earning really high. There might be someone who has really high experience but then doesn't really earn a lot, and then so on. But then overall, if you take a look over here, we can just have a basic visual overview to see that there is a kind of an increasing trend, right? So this is called a positive correlation. And this when we calculate the correlation coefficient, it would kind of be somewhere between -1 to +1. -1 to +1. And in this scenario, we might expect, let's say, something like 0.75 can be indicated as a really good coefficient. So 1, which indicates perfect correlation, is actually an ideal case. You'll never find a variable which should actually have perfect correlation. So anything between 0.75 is actually a very strong indicator of high correlation. On the same note, consider a scenario where you have negative correlation. So you take two variables. Let's say X would be an indicator of weight and Y would be an indicator of number of years lived. This is a hypothetical example, so please don't take it seriously. A typo over here. So it's generally observed that the more weight you have, or the more obese you are, the more kind of the more diseases or disorders you are a victim to, and generally it would translate to a less healthy lifestyle or a lower number of years of life. So if you try to make a simple plot over here, let's say let's say this would be 50 over here, and this would be 100. We just can't start at zero, right? Someone who's really healthy, we might say that he's going to live for more number of years. Someone who's a little more heavy or obese is going to live slightly less amount of years, and so on. This is a hypothetical example, and we might see something like this. We'll definitely see exceptions. We'll have someone who is performing in a different way. Someone who is obese but still has a very healthy lifestyle, and so on. So kind of you can expect a lot of out of the box cases, but then at a high level, you can kind of observe that there is a decreasing trend, which means that there is a negative correlation, which means that as weight increases, the other counter variable decreases, right? A negative correlation exists over here. So this might, let's say we have -1, 0, +1. You might find a negative correlation values tending towards this section. Somewhere, let's say -0.05 would indicate a highly negative a very high negative correlation between the two variables. Again, -1 is a very ideal case. We won't really find that. Now, in some cases, you might really have a relationship between both of them, but then two variables, but then looking at the number or the correlation coefficient, you might not be able to interpret whether there is any sort of relationship between the two. We'll get into this use case when we come to the programming exercise for binary analysis. So just after once we cover the explanation for the three different use cases, we'll actually get into the programming perspective example, and that's when we'll actually discover another scenario where just interpreting the correlation coefficient might not really suffice to understand whether there is actually a relationship between the two variables. So let's get back for now. We look into numeric and categorical use case. So what do we do over here? We have a simple bar chart. And the bar chart is used to showcase the average values of a numeric attribute across the different classes of the categorical attribute. So we've taken again a hypothetical example over here. This is again from the data set. So we'll say salary, which has three levels: low, medium, and high. There is a typo over here, please ignore that. And across average satisfaction level. So average satisfaction level is the numeric attribute, and salary is the categorical attribute. So what you're doing is you're aggregating the numeric attribute across the levels for the categorical attribute. I can see that, as you expect, high, which means that high band salary employees generally have a higher satisfaction level than the counterparts of low and medium. So we expect an increasing satisfaction level across the salary bands, and we kind of see that. But if you observe closely, you can see that the difference is, even though visually appears very high, it's actually pretty low. So it's 0.6, around 0.62 and 0.63. That's bare minimum difference between the three. But since the y-axis is organized with a different value, like it starts at 0.58 and ends at 0.65, so it's zoomed unusually high, and we get perspective which we don't really expect to comprehend the right way. So we look into Python example. So this is an output which we create from Excel. When we look at an example from the Python's Matplotlib or Pandas library, we get a better perspective to understand. We get a better perspective to understand how these two variables behave. So the last scenario we have, and one thing before we move on. So in this scenario, the aggregation metric might not necessarily be average or mean. In some cases, it can be sum, FUN sum, or it could be the maximum value or the minimum value or something else. It could be completely driven by the use case. But then by a general rule, you could actually say that most of the use cases, you'll always use average as the metric to aggregate across the different categorical levels. The last scenario, when we have both the variables as categorical. So what do we do over here? We actually look into the frequency distribution of one categorical variable across each level in the other categorical variable. So in this example, again we've taken a very simple example. We're trying to understand the distribution of salary segments across the sales department. So sales department has different categorical levels like sales, accounting, HR, technical support, and so on. And we're trying to see the percentage of different of the employees within each of these bands, which is belonging to the salary bands across each level. So you can see that sales has approximately 50% in the band low, then another 40% in the band medium, and then around 10% in the band high. So on, you can go. And if you take a better perspective over here, you just take a closer look, you can see management kind of looks different. So just using a simple visual inspection, using a stacked bar chart, you can actually look into the distribution of one categorical attribute across each level of the other categorical level. Now, in this scenario, we've taken a percentage distribution. So we might not necessarily take percentage distribution across all the scenarios. In some cases, a simple frequency plot will also do. So instead of percentage distribution in the stacked bar chart, we might have a simple stacked bar chart of frequency counts. So this was how we do bivariate analysis. So we have understood what measures, statistical measures do we take into account while we go ahead with bivariate analysis. And depending on the scenario of the kind of variable you're encountering, what kind of visualization tools would you use should help you to interpret or study the relationship between two variables of interest. So let's look into an example using Python code. I'll jump into Spider. Let's just print the different column names that we have in this data frame. Now, if you look over here, sales, which indicates different departments in the company, salary, which defines the different segments of salary, and left, which means they become employee leave the company, yes or no, which could be indicated as a 1 or 0 flag, and work accident might also be a flag like 1 or 0. Rest all of them are actually numeric variables. So satisfaction level, last evaluation, number of projects, average monthly hours, these are all numeric variables, and we have 3, or primarily we can focus on 2 for now as categorical variables. So to just take into account a simple example, we can explore the 3 different use cases where we have numeric and numeric, numeric and categorical with this dataset itself. So first we'll start with a simple categorical exploration. We'll take sales and salary into account. So in sync with the explanation we just had right now, what we would do is we would do a simple frequency plot using a stacked bar chart. Now we need to transform the data to actually be able to understand what is the frequency distribution of one categorical variable across each of the levels present in the other categorical variable. So let's go one by one. We'll start with the sales department. So df, we access the series or the column called sales, and we can just type in unique, and this will print the unique values inside that column. So we can see that, okay, fine, there are approximately quite a few values: sales, accounting, marketing, etc. What about the other one? So let's say we take the different unique values within salary. We already know the name, so but still we have low, medium, and high. Now we want to know what is the distribution of low, medium, and high across each of these levels. That's when we need to do a cross tab. Cross tab is analogous to the pivot tables, and pandas provides you a ready-made function to do cross tab. So we say pd, which represents the pandas object, dot cross tab. We pass in the first column of interest, that is sales, and we pass in the second column of interest, which is salary. And pandas will automatically create a cross tab for us in the easiest and neat format. Here we go. As we interpret this, we can have, let's say for the department technical, we have around 201 high paid and high salary employees, 1,372 low salary employees and 1,147 medium salary employees. Now, if you could actually do some more math, you can actually say sum 83 divided by 83 plus 609 plus 535 and calculate the individual percentages for high, low, and medium. But that is not necessary in all scenarios. Let's plot a simple bar chart to understand how do these numbers look like. Rather than going through and scanning each number, we can just simply plot a number and visually understand where do we have the highest distribution. So again, to visualize, we have two methods over here. One is a straightforward method which we learned earlier using matplotlib, or you also have a visualization library inbuilt within pandas. So if you just call in after this function, let's say you say plot and pass in the parameter kind is equal to bar. The default one is line chart, and you execute this. Pandas will neatly create for you a simple bar chart. Now you can see, okay, majority of the distribution actually comes under sales, and within sales you can see that low is the highest. So majority of the employees come under this category level. So rather than scanning through all the numbers individually, you can actually plot a simple bar chart and you quickly scan and analyze the numbers over here. But then we actually plan for a stacked bar chart. So what we'll do is we'll just add in one more parameter. Stacked is equal to true, and you can see here we have a stacked bar chart. If you want to actually create a percentage bar chart, I'll leave that to you. It's a simple switch you can actually add over here, or you can actually engineer the data and represent that using a stacked bar chart. But using this, you can clearly understand more about the two different categorical variables. You're trying to understand the relationship between two. So you can see that majority of the ones we have, majority of data actually falls under sales, and within sales you can see how are the different segments of salary looking like. One interesting thing, if you take a closer look over here, management, you can see that management has a good amount of ratio, a very good ratio between the three, like low, medium, and high salary employees. Almost all of them look like 33%, right? It looks fairly straightforward. Like there's a clean division between three levels over here. But that is not the case in the other ones. Have a look over here. The blue one, which represents the high salaried employees, form a very small part of the entire chunk. So this is how you actually visually inspect, interpret, and understand relationships between two different variables. Let's move on to the next example. You can actually do the same exploration using the matplotlib library also, but I would leave that to you. Please explore in your free time. Let's move on to understand the relationship between a numeric variable and a categorical variable. So I'll again just print the columns over here, df.columns, and I made a typo. Alright, so df.columns. So let's say satisfaction level would be our numeric variable, and we'll take salary as our categorical variable. Now we will need to augment the data to be actually able to go ahead with a bar chart. So if you remember, we need to aggregate the numeric attribute across each level of the categorical attribute. So if you remember in the data engineering exercises which we had in the previous module, we explored the group by function. We can do the same over here. Let's first create the data or augment the data in the right format. So let's just add a comment, numeric and categorical variable explosion. Alright, so let's say df, we say group by, and we pass in the group by index, which is in our scenario salary. So we want to aggregate across salary. What attribute do we need to aggregate? We need to aggregate satisfaction level. Here we go, and we pass in a mean function. So what you're doing basically over here is, if you have if you're finding it hard to recollect, you're finding the mean of satisfaction level across the different levels of salary. Now if you execute this, you can see that we get a simple plot, no, not a plot, we get a simple tabular format display for each of these values within salary and the corresponding mean satisfaction level. And the numbers are in sync with the example which I showcased in the PPT. You can see that low is 0.60, medium is 0.62, and high is 0.63. So the differences between them are fairly low, but then rather than just using these numbers to consume your insights, you can just do simply plot and then say time is equal to bar. It will help you visualize the data using a simple bar chart. And there we go. Now, since the y-axis is more well tailored, it starts at 0, it ends at the maximum value. It's easier to understand the true relationship across the different levels because it looks like, okay, fine, there isn't much difference. But had you fabricated the y-axis or had you zoomed into it, it would have kind of revealed some spurious insights. So this looks better. We're trying to understand the relationship between a categorical attribute and a numeric attribute using an aggregation metric of average across the different levels. Now, again, like I already mentioned, you could do the same using matplotlib, but then I would leave that exercise to you to explore on your own. Now we come to the last part, which is another interesting part in bipedal analysis. Here we explore two numeric attributes. So both of them, numeric attributes, we can actually understand the strength of these two numeric attributes using the correlation coefficient. So pandas by default provides you the correlation function. You say df.corr. Now rather than passing the attributes over here, what you can do is you can just say df.correlation, and correlation function will get into the depth of ds data frame. It will look into all numeric attributes and then give you a cross tab of all of them. Let's just explore this. You get a bunch of numbers over here. So as you can see, I had a cough. So the correlation between satisfaction level and across all the numeric attributes that is found in the data set. So left and work accident might actually be categorical variables, but then they are stored in the data set as 0 and 1. So accidentally pandas misunderstood that as a numeric variable. But then just ignore that. So you can see the satisfaction level across all of them. You can see the correlation coefficient. Now the correlation coefficient between satisfaction level and satisfaction level, that is between them itself, will always be 1. That's a perfect relationship, right? So you can see that trend everywhere. So time spent with the company and time spent with the company, it's 1. Now, if you look over here, you can actually go ahead and simply understand which two variables have a strong correlation between them. Now, if just a basic scanning through all of them, I don't really see something really very interesting. No, so this one looks fairly interesting. I would say number of projects has around like 0.41 correlation with average monthly hours. It kind of makes sense using the business logic, but then 0.41 is not really a very strong correlation, and I'm sure the plot might also not look very neat. So here I'll just use the matplotlib library as a tlt.scatterplot. And I'll pass in the x and y variables. Let's pass df, and I'll pass, let's say, number project. I need to add this. Yes, and I'll pass a second variable, which would be time spent with the company. Now if I look over here, I do simply plot, and I don't see any interesting results. Like this just doesn't make any sense. Let's try a different variable. Let's say number of projects, time spent with the company, and average monthly hours. Do we have a relationship over there? Not really. We don't really see anything interesting over here. So like I already mentioned, so while we're exploring bivariate analysis, the first part, like we're understanding what is correlation coefficient, I mentioned that if in case you find a correlation coefficient of 0.01 or 0.1, just looking at the value, you might tend to discard that because you assume that there's no correlation coefficient. There is no really any sort of relationship between both of them. But then it is actually important to visually explore using a scatter plot. I mean, try to understand the relationship between two numeric variables. I'll give you an example using the visual tool as a demonstration to help you understand how this works out. So if you consider an example, let's say that we have something similar to this one, like you have most of the points kind of in an increasing fashion. This is a strong positive correlation. and your number will also be representing the same. So let's say I'm just giving a random number here. So let's say you have a correlation of zero point 0.8, and this sounds pretty strong correlation. On a similar note, let's explore a scenario where you have strong negative correlation. So something like this, where you have multiple points kind of revealing a negative downward trend. This will also be a strong, relatively strong negative correlation. And if you try to calculate the correlation coefficient, you'll fairly find a strong number like let's say minus 0.75. This is just a random number, just for illustrative purposes. But then consider a scenario where you have a plot like this. You have an x and y variable, and you find something very interesting. So the trend increases to a certain point, but then after some point, it kind of starts decreasing. So you have a non-linear relationship between the two. Now this is kind of increasing first and then decreasing. So this is like a non-linear relationship. Now if you go to calculate the correlation between x and y over here, what happens is the increasing trend kind of negates with the decreasing trend, and both of them counter each other, and you get a very low correlation between them. So you might get a correlation of let's say something like 0.1 or 0.2, extremely low value. So just looking at the number, you might actually miss out that there is actually scope for a relationship, and there is some sort of relationship between the two variables. Now, there are a couple of correlation coefficients which while calculating the relationship, takes into account a nonlinear relationship also. But then the default one is in R Python doesn't really take care of that. So I would recommend you to go and explore this on your own. What kind of correlation coefficients techniques that are implemented in Python account for nonlinear relationship? Or let's just consider that you have two variables, x and y, and there is a relationship between them, but it's a non-linear relationship. That is, they might let's say the best example for here would be x would be age and y would be strength. So towards a point, and let's say this is like 10, this is 40, and this is 80. So while you grow till 40, you would have really good health, but then after that it kind of gets tarnished. So you see a relationship which definitely exists, and it's definitely a valid one, but then it's a non-linear one. And then you need a correlation coefficient which actually takes into account a non-linear relationship. So there are a couple of them. I would recommend you to please explore them on your own. So that's about the different bivariate techniques that we have explored till now. Let's just get back over here. We've explored, yeah. So we've explored what is bivariate analysis, what are the different scenarios that we need to consider. So two numerical variables, one numeric and one categorical variable, and probably two categorical variables. So what kind of statistical measures do we use to understand the relationship between the two? And what kind of plots or visualization techniques can be leveraged to study the relationship between the two? So just like univariate analysis, we've understood bivariate analysis and the kind of possibilities of exploration over here. So the next thing, which is multivariate analysis, is an extended version of bivariate analysis. A linear regression would be a classic example of multivariate analysis. But then we'll be taking up that in more detail in the next module, machine learning. So for now, we'll take a break over here. We take a pause and we stop with bivariate analysis. And we would move on to another important topic, which is feature engineering. So that's all with this topic. So we have reached the last part of the first section in this module. Feature engineering is one of the most important topics in the course of machine learning. And as you already know, like in a data science project or in any data science use case which we try to solve, a data scientist would actually devote majority of his time in exploratory data analysis and feature engineering. So what is feature engineering? By definition, feature engineering can be defined as the process of leveraging domain expertise to create features that help machine learning algorithms work better. Now, this process is extremely difficult and extremely expensive. It is an iterative process where we don't really have great results at the end of every iteration. And moreover, not every feature you would build will actually be useful in the algorithm. Before moving on, let's try to have a more layman view towards this definition. So, in a nutshell, feature engineering can be defined as a process of showcasing data or transforming data into a more informative format. So, to describe how does it work in machine learning, think about a scenario. So, just consider machine learning is the process of teaching a 5-year-old kid or a 10-year-old kid some sort of expertise or some sort of intelligence. So, how do you teach a child, a 10-year-old child, a 10-year-old kid, some sort of intelligence? So, let's say we give him a very hypothetical use case. A hypothetical use case is looking at a person in an office. Let's say you have a kid who is 10 years old, you've taken him to office, and in your office you have managers, you have individual contributors who are techies, and there are some corporate executives, and you are teaching a child to distinguish a person as a techie, let's say someone like a software programmer, a consultant who would be like more of an executive, or someone like chief executive officers or any chief executive officers. Your plan is to help your child understand and distinguish these three different kind of class of people. Now, you have been like helping a child understand this through simple techniques. Let's say you just introduce a child to your boss, saying that this is my boss. I work for him. His name is Andy, and he is X Y years, and let's say 40 years old. And let's say you introduce him to your colleague. You say, like, this is my friend Andy. He's like 25 years old. So the child actually tries to understand everything from the age perspective. So the first thing he would actually bring into his mind is, okay, the more age he has, the higher chances that he's a consultant or an executive. And the lower age he has, probably he's an individual contributor or a techie. So that's how information is provided. But then definitely he'll get confused at some point of time, right? So in some cases there might be a young executive who, let's say, would be an exceptional leader who is right now, let's say he's from the chief executive officer of the company, and he's probably 25 years old. So the child gets confused, like how his entire algorithm which he has devised in his mind to distinguish people has kind of gone wrong. So in this process, let's say you give him a clue, and the clue is, okay, if the person is wearing formals and a suit, most probably he is an executive. But the person, if he's wearing jeans and t-shirt, then most probably he is a coder or a techie. So with this clue, whenever his first algorithm fails with the age, he uses his second clue to actually get an understanding of whether the person is an executive or a techie, right? That's how the child kind of builds some rules in his mind. So what you've done over here basically is you have some sort of data and you've just fabricated the data or not fabricate, you've augmented that data into a better format so that interpretation becomes easy. So the child who was getting confused just with the age now finds it very easy with one additional clue. So feature engineering is the same process where we augment data into a format where interpretation becomes very easy. So for example, let's say um, you have, let's say I just showcase one example here. We'll definitely talk about a couple of more examples. Let's say the raw data looks like you have date and then you have total sales. So just the date won't actually deliver anything meaningful to an algorithm. But then what if I extract the weekday from this date? So let's say the weekday is Saturday, Sunday, Monday. And if I take a look at this closely, I can see that Saturday and Sunday, the sales have actually gone about 300,000. Same is the case over here. We have Saturday and the sales have gone about 300,000, which kind of makes sense because majority of the shopping any corporate or any working professional would do would be dedicated towards the weekend. So you would see limited traffic from Monday to Friday, and majority of the sales and traffic driving on Saturday and Sunday. So instead of just passing dates, if we try to represent this date in a more informative way, that is weekday, you would actually have that data being more useful for the algorithm. So algorithm finds it easy to find patterns using weekday as a column rather than date as a column. Now similarly, instead of weekday, you can actually just create number of week also. Let's say 21st of Jan is probably the third week of the year. And let's say something like 31st of 25th of March would be something, let's say like 25th week of the year or something like that. 25th, it's not a 25th, I'm just like giving a random number over here. Or actually, you could actually use month also as a variable. So it's observed, like you can see sales booming up during Diwali, during Christmas, during other seasons. So month is actually and also a great indicator to actually go on. In some cases, you might have a flag, whether it was a working day or not. So in India, we have, let's say, around 15 to 20 important days identified as public holidays. So generally, people would go for shopping on these days because they're free. So just having an indicator like a working day or not, that is also an informative variable. So these are different types of features. Just from the date variable, you can actually go ahead and create around like 5 to 10 different features. One could be weekday, one could be the week number, one could be the month, one could be just the year. Assume you have data for, let's say, 5 years. And there would be one year where there would have been some sort of depression and the economic crisis would have actually like percolated into the pockets of anyone, which would have translated into lower sales. So year will also be an important number to actually add over there. Not in all cases. Let's say you just have 1 year of data, then adding a column for the year will make no sense. So this is how you represent data in a more informative way. Just like you gave a child a simple clue to understand that information more easily, you're giving the algorithm an information in much more concise way. So what could be some other techniques we could actually leverage over here? So here are a few techniques. Now, unfortunately, machine learning and feature engineering, I mean, they don't really have a concrete set of processes or rules where you can define, okay, fine, these are the most popular or the most concise or comprehensive versions of feature engineering processes. If you follow this, you cover the entire exhaustive list. No, we don't have something like that. We don't really have the luxury of jotting down some rules and saying this is the most exhaustive list which we have. Here we have a few, and the rest is something which you actually develop with a lot of domain expertise. Now, why domain expertise? Because information can be made more concise and you can actually add more features only when you understand the domain to a great extent. Now, if you tie that understanding with this example, so this is raw data for sales. So let's say I'm combining this data or I'm comparing this data for a retail use case. Now, in a retail use case, you are aware that Saturday and Sunday are probably the days when maximum sales will happen, or weekend or holidays, or let's say or holidays or Christmas and Diwali is the time when actually maximum number of sales happen. So this is something which you know because that's intrinsic to the retail domain. That's when you have some sort of domain expertise. So tomorrow, when you're solving a problem for, let's say, an airline, or you're solving a problem for the financial industry, the domain expertise you would have over there would be different, and the features over there which you would create over there would need intrinsic knowledge of that domain. So it's completely business dependent, and it needs a lot of research to actually come up with some great features. Some features might not really be very informative or useful, so it takes a lot of iterations to try, understand, combine, and then see whether it works out or not. Now, I'll just enlist a few of them, how we could like take feature engineering or practice feature engineering in any general scenario. The first is pairwise differences. So let's say you have a data set with 10 columns and 100 rows. So each row is a sample. Now, pairwise differences is basically the difference between two columns. So when would this be ideal? So let's say you're talking about the same use case, retail. Now you have two columns. One would be the revenue and one would be the cost. And now you want to kind of understand profit as a scenario. So a machine learning algorithm won't really understand, let's say if it's a tree-based algorithm, it won't really understand that profit is more important. So combining the two, revenue and cost together, and then extracting profit from that is something which is beyond the capability for an algorithm. In some cases, it might learn, but then it's easier or it's better to actually make it more explicit. So if you just do a simple subtraction between the two columns, for each row, if you subtract revenue minus cost, and cost from the revenue, you'll actually get the profit. Now this profit is actually a better representation of the revenue of the number over there. So let's say if you're trying to predict some other thing, something else, something let's say like um, like a high value customer. So in that high value customer, profit would be more valuable than actually just revenue. A customer who gives you more profit, let's say he might buy 10 products and each of those products might return you $1. But then for the same amount, a person can just buy 10 products and he might return you $15. So there's more profit over there, and that customer is more valuable. Now, identifying this helps us train the model in a more effective way. Log transformation. Log transformation helps you kind of reduce the weight of higher value. So, for example, uh, let's say you are trying to build an algorithm where you want to understand or you want to predict. Let's say you have a company or you have a startup and you want to give stocks to your employees, right? So when you want to give stocks to your employees, you would have created a formula. In that formula, you would have considered the number of years of experience you have, the total amount of salary you withdraw, then the time when you join the startup. So generally, people who join a startup early have taken a bigger risk. So the risk factor is becoming something which is more important. Now, what happens is if you do a simple multiplication and you say that, okay, the number of years of experience as it increases, the stock increases by some X percentage. So that will not be really a fair way to deal with stocks. So let's say someone who has joined you with 5 years of experience might be getting, let's say, 100 stocks, but someone who has joined you with 10 years of experience or 15 years of experience is not necessarily worthy uh, 50 like three times the stock which the person is getting with 5 years of experience. So you need a logarithmic or smoother curve. So let's say someone who's joined you with 5 years experience gets 50 stocks. Someone who's joined you with 50 years of experience might get, let's say, 75 stocks. So to make it more smoother, to make the curves less steeper, you use a log transformation. Similarly, square or cube of an attribute. In some cases, a smaller increment is okay, but a larger increment is extremely bad. So let's say something like some medical conditions monitoring uh, the presence of toxic, like some toxic material in your body. So at lower levels, it's still fine. Your body is immune. But the moment it increases by a small factor, the kind of if after effects or consequences it will have will be really dangerous. So you need to indicate that a small difference is okay, but a bigger difference is really bad. So you just need to multiply or amplify that differences. So that's why you take a square or a cube, or you can just go on as long as you want. But then mostly you can just settle down with square because you get positive values. So if you take a square and let's say I'm saying something like, let's say the presence of toxin is around 2%. So that number gets converted to 4. But then let's say the presence of toxicity is around 5%. That number gets converted 5 square, which is 25. So 2 corresponds to 4 and 5 corresponds to 25. You can clearly see the difference that when the number is 2, the impact is 4. When the number is 5, you've amplified the effect to 25. So the algorithm automatically learns to understand that when is it more important and how do I need to treat this variable. Pairwise products, this would be a simple scenario where you combine a couple of categories. So for example, let's say you have a retail outlet, and in your retail outlet, you have various descriptions for a product. So product belong to a product family. It could belong to a product manufacturer. It could belong to a product type, then, and so on. Now, product manufacturer could be, let's say, Apple, Samsung, and Nokia. Product family would be mobile phones, laptops, let's say tablets, and so on. So when you just consider a manufacturer as a single attribute, things might not be very informative. But then when you combine, let's say, two different categories together, so you combine manufacturer, and the type of electronic device or the type of product together to create a cross product, a combined product. That might be more effective. So you combine two variables, you create a pairwise product that might be more effective. The same could be the case with any numeric variable. Let's say two numeric columns or attributes will not make sense or will not add a lot of value just by individual columns. But when you multiply it, some latent features get combined and the machine learning algorithm starts detecting some patterns which might be really important and helping it identify the patterns easily. So pairwise products can be done on a categorical variable and on two categorical variables or on two numeric variables also. Last would be reducing noise in the categorical level. So let's say you have type of product as a column, and this type of product would, let's say, have 100 different categories. It could be mobile phones, it could be bags, it could be let's say electronic devices, then it could be grocery, and so on, right? So if you go to an e-com website, let's say from something like Amazon, and if you go for shop by category, you can probably see hundreds of different categories over there. So what happens is majority of the data might go into only a couple of those categories. There are few categories where the total amount of data that falls into these categories will be very less. So to reduce noise, what you can do is you can just regroup them. So let's say if you have 100 categories for one attribute, you can just probably reduce that to 10 or 15. How do you reduce that? We have two ways. One is the data way, the other one is the business way. Business way would be if you have domain understanding of that problem, you can probably combine a couple of groups together to form a single larger group, right? Let's say you can just say, let's say all the electronics come under the tag electronic devices, and grocery would be a larger bucket with all the different types of grocery under that bucket. So you would regroup them based on your understanding of the domain. But then let's say if you don't have domain level understanding, you can actually go the data driven way. Okay, let's say if you have 100 different categories, you can just look at how many categories contribute to around 80%. Generally, you can observe that 80% of the data will actually be focused around 10% of the categories. So if you have 100 categories, probably 10 of them, if you just consider 10 of them, that will be the major part of the data. So you keep 10 of them as it is, and rest everything you group them as others. So just like everything else is combined as one new category, and you'll have total 11 new categories. 10 which were already there, which was the major part, and rest everything as one single others. So these are simple ways to actually go ahead and augment your data to a more informative, in a more informative way. This is definitely not exhaustive, and I might not be able to like give you more examples. I mean, we can definitely talk about examples, and this might go on, but then that might not suffice for you to actually help for you to use feature engineering in your use case. You tomorrow you might be having a use case, and if you want to do feature engineering with that, you would definitely try all these basic steps. But then beyond that, you would need to understand the domain. You would need to do this a lot of iterations with several other combinations to see what actually works and what does not work. So in the last module, that is the fifth module, when we take up a capstone project, we look into a use case where we can do feature engineering by combining some domain knowledge which we can which we would have for that problem statement. That's it for now. Let's move on to the next section, an introduction to statistics. So let's begin with section 2, an introduction to statistics. Before we begin, I would like to put forward a small disclaimer. So statistics is a really vast topic, and covering each and every concept from this subject is beyond the scope of this course. So what we would do is, we would cover a couple of few important topics that will be required while we go ahead in the next module of machine learning. We learn those important topics with a bit of abstraction. Like I presume most of the users who would be watching this video tutorial would not be having a math background. So I'll abstract the math and I'll just put forward statistical concepts with layman terminologies so that you can understand them as simple concepts. Definitely you would need to do a little more reading in case if you have basic understanding, like if in case you miss out some understanding of math. I would highly recommend you to read up some material before we move on to the next module, machine learning. So let's get started. We will cover a couple of very simple terminologies that you've probably come across already. Here are a few basic terms, and I'm sure most of this is something which we have already learned. We have three different sections over here: measures of central tendency, measures of variability, and the normal distribution. And most of this has somehow been already discussed to a certain extent in the previous slides. So let's start with measures of central tendency. We have three simple terms or three simple measures that fall into this bucket. That is the mean, median, and mode. We already know these concepts. Mean is basically the average of the entire sample or distribution. Median is the 50th percentile or the middle value in the entire sample. Mode is that value which occurs most frequently in the dataset. So let's say, I think we've not covered mode previously. So let's say, to give an example, consider 100 students, they have given a test and we have 100 scores. Now if I tell you mode, let's say around out of 100 students, around 35 students, or let's say around 25 students have scored 65. And 65 is the most frequent number in the dataset. That would be the mode. So mode is basically the most frequent number that occurs in the sample or the data set. Now, just using these three, mean, median, and mode, can kind of get a fair understanding visually of the central tendency of the plot. And to understand the variability, that is dispersion, we have range, variance, and standard deviation. Range is basically, as you already know, maximum minus minimum. So you understand where does this plot start and where does the plot end. Variance and standard deviation, as we already know, are simple measures of data dispersion. How spread is your data? So standard deviation is a follow from variance. Standard deviation is a square root of variance. And standard deviation and variance standard deviation is basically the most popular statistical measure used to study data dispersion. Moving on, we have the normal distribution. Normal distribution is one of the most important distributions in statistics. It has different properties that make it really unique and extremely useful for further analysis. So what are the properties of a normal distribution? Now, you would have probably already heard it, and we've given a small demonstration in the previous slides. It's called a normal distribution, and it looks like a bell curve because it kind of resembles a bell shape. Now, what are the properties? It's symmetric around the mean, it's unimodal, and it's asymptotic. Which, when I say it's symmetric around the mean, so the mean would be at the center. Let's say this is the mean. And if I cut this into two halves, the first half and the second half would look exactly the same. That's why it's symmetric. It's unimodal, which means that there's only one value which occurs very frequently, and that most frequently, and that comes in the middle section. So if you observe over here, we have the values 140, 160, right? And if you look at the middle bucket over here, this one, this is that value which occurs most frequently in the data set. And if you just probably we have used a bucket of 10, like bin size is 10. But if you use a bin size of 1, let's say you just plot the frequency of one single value, you'll still see that the frequency is so high that it comes as in the middle as a center point, and it lines up as a single partition which divides both of them in two halves. So in the normal distribution, we have the property that we have the mean, median, and mode as the same. So let's say for this 150 would be the mean, 150 would also be the mode, and the middle value will also be 150. That's one property of the normal distribution. And another point, it's also asymptotic, which when I say asymptotic, now this is a histogram, but then when you, let's say, plot a simple plot, you can actually see that the lines over here never really touch the axis. It kind of, it runs as a never-ending, like it doesn't really touch the axis. It just keeps running as parallel lines towards the end, and it is completely determined by the mean and the standard deviation. Now, why is the normal distribution so important? It's because of the characteristics of the normal distribution that we can actually rely on the ground truth and use a lot of probability statistics. Now, this is where we have descriptive statistics and inferential statistics. So what happens is, let's say you're trying to do a simple analysis. You're trying to see what is the average height of men in a country like India. So let's say you have a population of 1 billion, around, let's say 50% will be men, and you don't really have the luxury to go and measure the height of all 50 billion people, right? So what you do is you actually take a simple sample, which is, let's say, around like 1,000 men or 10,000 men based on some analysis. You'll stick on to this 1,000 member sample or 10,000 member sample, and you would get the numbers which will actually have some mean, median, mode, and the variabilities over there. Now, since we have a normal distribution with some specific properties, we can do inferential analysis, which means that, see, basically, let's say if you have a sample of 10,000 members, and it might be a true representative of the overall sample or overall population, what makes you 10% sure that the sample's mean is actually the population's mean? So how can you be so confident in saying that, okay, you just measured height of 10,000 people in India, and you've got a number saying that the average height of men in India is around 5.7, 5 feet 7 inches. How can you say confidently that the average height of all the men in India are actually 5.7? So we have two terms over here. We have the sample and the population. Sample would be the 10,000 member group, and the population would be all the men in the country, which is India. So that is where we have the normal distribution in the picture. In simple terms, the normal distribution, because of its properties, allows us to make inferences about the population from just the sample. I'll not get in the depth of it. We move on to a very important term, the central limit theorem, which will help us understand this better. So, central limit theorem is a statistical theory that states that given a sufficiently large sample size from a population with a finite level of variance, the mean of all samples from the same population will approximately be equal to the mean of the population. If we break this down to a more layman explanation, we can say the mean of the sample is more or less equal to the mean of the population, which means that when you have a sample, and if you calculate the mean of the sample, and the sample size is sufficiently large, and all the criteria mentioned over here are actually met, you can actually infer that this mean, which is of the sample, is actually very close to the mean of the population. That's how you make inferential statistics based from a sample. So instead of going ahead and calculating the mean for the entire population, which is not the possibility, you have a sample and you go ahead and calculate the mean of the sample, which helps you understand that this is really close to the mean of the population. And also, samples will follow an approximate normal distribution pattern, with the variances being approximately equal to the variance of the population divided by the each sample size. Similarly, we have another important topic, z-scores and standard error. Now, what is z-scores? Z-score is nothing but a standard score. Now, to put in simple terms, let's say if I give you basic numbers, let's say something like out of 100 students, on an average, let's say one student has scored around 75. The score obtained by one student in the test is around 75. And let's say when I give you the mean also, the mean is around, let's say, 65. You will have a fair amount of idea that basically this person is somewhere above the mean and then below the maximum level. But then you still don't have concrete idea about how does this student fare with all other students. Like where does he stand in the entire class? What is the percentile that he's obtained? Now, if you look over here, you won't really have an idea where does the score come? Does it come over here? Does it come over here? You'll just have an approximate idea. Or in some cases, let's say if I just don't give you the mean, I'll give you just a number. It becomes extremely difficult to understand how does the student perform in comparison with all his peers for the test. Now, z-scores is a standardized score which will help you to exactly understand how does one student, with the help of z-score, how does one student perform in comparison with all other students. Now, let's say it's as simple as, let's say if I give you a z-score, you will say, okay, fine. With that score, I can say that the person has somehow reached this point, which means that he's approximately 80th percentile in the classroom. So let's get into depth. Z-score has the formula, I'll say z-score is equal to the raw score minus the mean upon standard deviation. Now, if you try to interpret this value, I'll say z is equal to raw score minus the mean upon standard deviation. Now, this actually helps us understand how many standard deviations is the score above the mean and below the mean. So if the z-score for a student is around, let's say, 1.5. Now this would be interpreted as this person has scored around 1.5 standard deviations above the mean. And you can fairly get an idea, okay, let's say if this is normal distribution and this is the mean and 1.5 somewhere here, you'll get a fair amount of idea that this is where a student has performed with respect to the entire classroom. So z-scores help us interpret the percentile values for each value in a sample in a very easy and layman way. So here we can see a basic z-score sample. Over here it's -2, this is 1, 2, and 3. So a person who has scored somewhere over here would be 3 standard deviations away towards the right from the mean. Similarly, he would have scored less also. Let's say he has a standard deviation z-score of -2. So his score is basically 2 standard deviations below the mean. So we can have a score of plus and minus, and this will go up to standard deviations. But then the moment you cover up to 3, we have approximately 99.9% of the entire of the entire sample covered. So that's z-score. Similarly, we have another important metric, a statistical measure called standard error. Standard error is defined as the standard deviation of the sampling of a statistic. I know this might sound a little confusing. Let me give an example. So let's say the example over here is sampling distribution of the mean. Now what happens over here is, let's say you have a sample of 100 members, and or let's say you have a population of, let's say, around, you have a large population of around 10,000 samples, 10,000 records, or 10,000 training samples. Now, what you do is you actually take a smaller sample, or let's say of 100 rows, and you take a and you take a mean of that, and you repeat this process several times. Now you have, let's say, 1,000 rows. Out of 1,000 rows, every time you take 100 rows, take a mean. Again, you take a sample of 100 rows, take the mean of that, and you make a note of it. If you repeat this process around 10,000 times, you will have 10,000 values for of mean of that entire population, right? Of the sample. Now, for these 10,000 observations that you have noted down while taking your sample and the mean, if you plot that, that would actually be the sampling distribution of the mean. I'll just paraphrase this. So let's say you have around 1,000 records, and out of these 1,000 records, you take around 100 records to form a sample, and you calculate the mean. Let's say the first time you do this, the mean was around 6.5. Then you again take a random sample, and you again take the mean. Now let's say the sample's mean was around 6.9. And you repeat this process. Every time you note the sample's mean, and you repeat the process again. And you repeat this around 10,000 times. So at the end of this exercise, you'll have 10,000 different values of mean. It should be, let's say, 6.5, 7.5, sometimes even higher, 8, or something like that. Now, if you do a distribution of these records that you have calculated, that these 100 values will be 1,000 exercises give you 1,000 values of mean. And if you do a plot of these 1,000 values, that will actually be the sampling distribution of the mean. Now, had this exercise been done with some other statistic, let's say instead of mean, you would have taken the mode, or the median, or something else, or let's say something like minimum, maximum. You would normally use mean as the most common thing. You'll also use in some cases some other statistical measure, but then most probably you stick around with mean. Now that's why sampling distribution of the mean, because it's actually several samples taken to calculate the mean, and then you have a distribution of the mean of those samples. Now, what is standard error? Standard error is the standard deviation of the sample. So if you go and paraphrase, you have 1,000 records, you take a sample of, let's say, 100 records, you calculate the mean, you repeat this process around 100 to 1,000 times. So you have 1,000 values of a mean, and you do a plot of that. That's the sampling distribution of mean. And then you take a simple standard deviation of that distribution. That is the sampling distribution of standard deviation of the sampling of a statistic. So of a statistic over here is the mean. That's why the standard deviation of the sampling of mean. I know this might sound very confusing, or it's a very long statement to understand, but then at the end, this is a simple way to understand how much standard deviation does your sampling distribution have. And that helps us understand the stability of a particular parameter or a value. We'll be using the z-score standard error together a lot while we do statistical modeling like linear regression, logistic regression. We can actually understand, let's say if I give you the beta value. Beta value is basically a coefficient of a variable, and I'm saying the standard error of this beta variable is a value. Now with that value, and if you take the mean, you can actually understand how stable these values are. If there's a higher standard error, you can fairly understand that there is a lot of variations in the samples. You don't really have a lot of stable values. You can't really trust these values. So this is basically useful to understand how stable, or how stable your actual value would be. That's standard error. We now move on to probability distributions. So we have reached another important topic in this course, probability distributions. Let's start with a very layman approach again. What is probability distribution? In a nutshell, it can be defined as a statistical function that describes all possible values and the equivalent likelihood or probability that a random variable can take within a given defined range. Now, this random variable can actually be a categorical variable or a numeric variable. Now, basically, where do we use probability distributions? They have a lot of use cases. So let's say an investor might use a probability distribution of a stock to assess the possibilities of returns that stock may have in the future. If it is a high risk, he might generally tend to not invest in that. But then there's a high probability that he might get good amount of returns on that stock. Then there's a very high chance he might go ahead and invest in that. Similarly, an insurance company would like to assess what is the chance that a person might actually meet an accident in a specified time range. So, based on various factors, we understand the chances of getting into a situation where the accident might happen, calculate the risk, and then take an action based on the kind of assessment they have. So, how do we do this? We have a simple assessment over here. Let's say in the second example over here. What we're doing is we're trying to showcase the probability distributions for the sum of two six-sided dice. So a single dice, which is let's say fair dice, has six sides and it will have values from 1 to 6, and you have two of them. Now when you roll two of them, and you're trying to look at the probabilities of the different values that make an outcome, which is the sum of those two dice. So when you roll two dice, you can have values like either the least value would be 2, so that which means that both the dice will have a 1 and a 1, and the maximum would be 12, where you'll have a 6 and a 6. And it could take any value. It could take around like 4 and 5, it could take 6 and 3, it could be a combination of any of the six numbers for the two dice. Now, if you try to build a probability distribution chart for this use case, what we would have on the x-axis would be the list of all possible outcomes for that use case. Now, what are the different values? So in this case, the value would be sum of the values from two dice. Now, what is the distinct set of values that the dice can showcase? The least will be 2, that will have 1 and 1, and the maximum will be 12. You won't have any values which will fall outside this boundary. Now, what are the different possibilities of getting a value like 6, a value like 8, a value like 10, right? So let's say, now this is a very basic example. Let's say you want to understand, you're playing a gambling game and you're rolling two dice, and your friend is asking you to bet, okay, and you place a bet that, okay, if the sum of this of the two dice is around 7, then I would like to place a bet for $100, right? And now, if you can actually look over, you can see that the chances that you get the number 7 is very high. So anything above 7, anything below 7, you have your own assessment of the use case. So over here, for this dice example, let's say you have two dice and you have numbers 2 to 12. What are the chances that the number will end up being 2? What is the probability of the dice showcasing some of the values as 2? So you'll have just one scenario. If both the dice will have the values 1 and 1, and out of total 36 outcomes, if you roll two dice, 6 sides and 6 sides, so you have total combinations of 36 different values. So only one out of those 36 combinations can actually give you a value of 2, right? So that is the probability over here. We have a value of 1 by 36. Similarly, for 12, if you only have 6 and 6, you'll have the probability value as you'll have the total as 12. So the probability of that is also 1 by 6. What are the chances that you'll have a sum as 6? You could either have a 2 and a 4, you could have a 5 and a 1, you could have a 3 and a 3. So if you add all the possibilities of getting that by the total number of possibilities, you get the equivalent probability of getting a 6. So this is basically how you can interpret a simple probability distribution. Now there are various different types of important probability distributions. Let's have a look at them. These are just a few of them. Now the normal distribution, something which you are already aware about. You would actually want to assess what are the chances that a student will score about 80% in the test. So looking, or let's say some score in the test. So looking at the normal distribution, we can just find where does a student, what are the chances that a student will actually score above 80, or between 50 to 60, or between 55 to 75. So that's a score which you can assess and take a risk accordingly. Then binomial distribution. So binomial distribution is actually used in scenarios like, let's say, you want to understand what are the chances that if you flip a coin 10 times, what are the chances that you get straight 10 times heads, right? So different types of use cases where you can understand where a binomial distribution can be useful. So over here, this is a scenario where you have flipped a coin 2 times, and what are the chances that you got a head 2 times, right? So these are the possible outcomes. One is you have 0 outcomes of heads, that is both the times you got tail. One is you have one time, at least one of the times you got a head. In the last case is both of the time you got a head. So what are the probabilities of getting a 0 head, 1 head, and 2 head? You have a distribution of all those outcomes over here, and then you can take a risk. So generally, companies take this kind of distributions to understand, assess the risk associated with certain events, and then take a call. Similarly, we have a normal distribution. Normal distribution can actually be the same one which we referred earlier. So instead of 2 dice, just assume we had 1 die. So what are the possibilities of getting a specific value? Now, if it's a 1 die, the probability of getting any side is 1 by 6. So in that scenario, all of them will have a value of 1 by 6. Simple, plain, uniform distribution. And there are definitely a lot of more, and they have valid use cases where you can actually go ahead and find when this happens. There's another famous distribution called the Poisson distribution, written as Poisson, but it's pronounced as Poisson distribution, where you can go and find out the possibility of, so let's say you have a call center, and this call center you are trying to understand the total volume of calls that happens every day, or you're trying to understand the total number of accidents that happen on road every day, and you want to find out the total number of days that will be required to, when X number of accidents will happen. Scenarios like that will actually be easily modeled using a simple probability distribution. So that's about probability distribution. We move on to the last topic in this module, which is one of the most important ones, and we'll be using it extensively in the next coming module too. It's called hypothesis testing.